In this video, I just want to do a few homework problems just to help you with a review for the test and look at some of the types of problems that from your homework that might show up on the test. So the first one is to find the vector x determined by its coordinate vector x sub b, where b is the basis of the vector space. Now remember, a basis of a vector space is just the building blocks of a vector space. And so ideally, every vector x can be written as a linear combination of the vectors in the vector space. So basically what we have is if I take a multiple, certain multiples of the first vector in the basis, plus another multiple of the second vector in the basis, then I can form the subvector x. And the coordinate vector basically is just the coefficients in front of each of the basis vectors. And so this means that x can be written as 5 times the first vector plus 3 times the second vector, and that means we're going to have negative 17 as the first coordinate of x, and then 10 as the second coordinate of x. So you can kind of see every basis or every element can be written according to the basis, where the coefficients of the expansion are called the coordinate vector. Now we're asked to find the coordinate vector given the basis vectors and the vector in question. So remember, if we have that x is 0, 7, if we're asking for what the coordinate vector is, basically what we're asking for the coefficients that when I multiply times the basis elements give me the vector. So if x is a linear combination of the basis elements, then the coordinate vector is given by the coefficients c1 and c2. So we want to find what c1 and c2 are. And we can see that this gives us a system of equations when I think about that linear combination. Alright, so we're trying to find C1 and C2. There are a lot of different ways that we can solve that system, but let's just use an augmented matrix. We could do elimination, we could do substitution, Cramer's rule, but let's just use our Gaussian reduction. And when we do that, let's see, our first row is going to give us 1, negative 2, 0. And then it's going to negative 2 times the first row plus the second row is going to give us 0, 7, 7. Okay, and then we want that leading 1 in the second row, so multiply times 1/7 to get 0, 1, 1. And then to get that last 0, we multiply the second row by 2 and add to the first row, and we get 1, 0, 2. So that's going to give us a C1 equal to 2 and a C2 equal to 1. And so our coordinate vector of x with respect to this basis b is equal to 2, 1. And remember, I'll just say that now because I thought of it, but don't forget that vector space can have multiple bases. Bases are always going to be linear independent vectors, and they're always going to have the same number of vectors. So you could have more than one basis, but they're all going to have the same number of vectors in the basis. And the coordinate vector according to each basis is going to be unique for every vector. So although there are multiple different bases, when you talk about the way that a vector x can be written according to a specific basis, there's only going to be a one unique coordinate vector relating to that. Okay, we're asked for this particular subspace. How can we find a basis for the subspace? And it's very easy if we see that all vectors are of the form s minus 7t, s plus t, and then 9t, then all vectors can be written as s times 1, 1, 0 plus t times 7, 1, 9. And so, since all vectors are the linear combination of these two vectors, then the basis, or a basis, is given by the two linearly independent vectors. So that's a basis, and our dimension is 2. Okay, a vector space of this form basically all consists of all vectors of the form A, B, C, D. That can be written this way, and we can just, all right, so A is dependent on B and C, so it looks like B and C are free variables. We'd say A equals 5B minus C, and B is free, C is free, and there's also no stipulations on D, so it is also a free variable. And what we do is just say, okay, all vectors can be written as B times the matrix 5, 1, 0, 0, or the vector 5, 1, 0, 0, plus C times the vector negative 1, 0, 1, 0, plus D times the vector 0, 0, 0, 1. So we have 3 free variables. That means that our dimension is also equal to 3. And our basis would be just consisting of those 3 vectors. Problem 14 asks us to find the dimension of the subspace spanned by the 3 vectors shown, and then find the dimension. Now, the h is defined to be the span of the following 3 vectors, but if we look closely, it's actually overkill because notice that the second vector is 3 times the first vector. And in fact, the third vector is 2 times the first vector, so they're not linearly independent vectors. And in fact, we could take any one of them and say that h is equal to the span of, any one of the vectors. We'll just take the first one because it's the most reduced. And then the dimension of h is equal to 1. So make sure when you're dealing with multiple vectors in a span, you check out that linear independence. Another way to do that, if it weren't so obvious, and say it were 3 3 by 1 or 4 by 1 vectors and you can't automatically tell, is just set them up as the columns of a matrix and then reduce the matrix, and then the number of leading ones that you have is going to give the dimension of the matrix, or the dimension of the vector space. When you're asked to find the dimensions of the null space and the column space, the easiest thing to do is for the dimension of the null space, that's just the number of free variables that we have. And so since we have a free variable here and here, that's 2, so we will say the dimension of the null space of A is equal to 2. And then the number of linearly independent column vectors that we have is going to be the dimension of the column space. And so you just look at how many leading ones do you have? And that would be 3. Okay, we talked earlier about the rank, which is the dimension of the column space versus the dimension of the null space. The rank of a matrix is the number of linearly independent columns that we have. And so we would reduce it, which they've given it in reduced form, and we see that there are 2 linearly independent columns, the first 2, and so the rank of A would equal 2. And the dimension of the null space is given by the number of free variables that we have, and since we have 2 free variables, then the dimension of the null space is also equal to 2. Now, if we're asked to find basis for the column space, the row space, and the null space, let's just start with the row space is basically just the set of all linearly independent rows of A. And to determine the basis for the row space, and we didn't spend time on this, but basically there's just a theorem that says the basis for the row space of A can be found when you reduce it, the number of rows that you have with leading ones. And so the basis for the row space of A is just given by, and then remember, think about rows are a row space consists of linear combinations of the rows, and so we'll list these as horizontal vectors, and we would say the basis of the row space of A is given by the linearly independent rows, and so we just write it that way, and those come from the reduced form. And then the basis for the column space of A, we just look, where do we have pivot rows or pivot columns, and these are the first 2 columns. So we actually go back to A and we list the linearly independent columns corresponding to those leading ones. Oh, that second one's negative 27. Okay. And then the way we find the basis for the null space is like we've done before. Remember the null space, I'll go over here to do that. The basis for the null space, when we reduce it, think about if we were saying A times an unknown vector that I'll call x1, x2, x3, x4 equals 0. So we're looking for solutions of ax equals 0. And so what values of x satisfy that relationship is what we're asking. And so if we were to reduce it with a row of zeros, then what we get, or excuse me, a column of zeros, what we get is x1 is equal to 3x3 minus 6x4. So x3 and x4 are our free variables. And then we could say x2 is equal to negative 2/3 x3 plus 2x4. And so the basis of our null space would be x1, x2, x3, x4, where we get 3, negative 2/3, 1, 0, and then negative 6, 2, 0, 1. And we get that from, here is our solution form over here.